never do that? No.
Okay, I don't know if we're gonna get through this whole section today, but we're gonna try. If not, then we'll finish it up on Wednesday and do the other sections, and anyway, we're gonna be done by Friday. That I promise you. So we got five sections to get through this week, so we just done one, we're gonna start this one, see if we get through it or not, and then we'll kinda go from there.
Do you want to start the one on Math Excel for this?
Absolutely, absolutely.
No, we won't.
Okay, so starter questions, can we handle those without me actually doing them?
Yeah.
Okay, if you can't graph y equals 2x plus 3, you need to leave this classroom right now, because you're gonna fail the final.
Okay.
No,
We just went over.
not a line.
Oh, that's.
Okay, what about now the cube root of x could be a little tricky, all right, but let's think of some smart points to pick for our x and y. Let's do a little xy table here. Yeah, we like 8. We like 1, we like 0, we like -1, we like -8. So what's the cube root of 8? It's 2. What's the cube root of 1? 1. What's the cube root of 0? 0. What's the cube root of -1? -1. What's the cube root of -8? -2. Okay, let's plot those points. So we have 8 and 2, and I'm going to kind of guess here. 1 and 1, 0 and 0, -1, -1, and -8 and -2. So cube root looks something like this.
Wow. From the new century.
I remember.
All right, now if we want to find the inverse functions, how do you find the inverse? You do what with x and y? Switch them and solve for y again. Okay, so on part A, if I wanted to switch that, I would have x equals 2y plus 3, and then I would solve for y. So I would minus 3. So I get x minus 3 equals 2y, and we divide by 2. So we get y equals x minus 3 over 2. That's the inverse of the first one. Now the second one's even easier, believe it or not. So again, switch x and y. So we get x equals the cube root of y. And how do I get rid of a cube root? Cube it. Yep. So we get y equals x cubed. There's the inverse of cube root of x. Okay. Now they want us to graph part 2. So all you have to do is just switch x and y to graph it, right? And again, we're not worried about lines because the lines are easy. So on my cube root of x here, so I'm just going to switch x and y. So instead of 8 and 2, I have 2 and 8. So I have this point right here. I should do that in a different color. Instead of 1 and 1, I have 1 and 1. 0 and 0, 0 and 0. -1, -1, -1, -1. -8, -2, -2, -8. So now that one looks like this.
Do they cross like perfectly in the middle?
No, they don't. These these touch. The red one kind of comes down this little way and then like that, and the black one will come like more like this and up and like that. But that's hard on our very non-accurate graph to show that. But yeah, they don't. I mean, those 3 points match up exactly, but the points in between them don't. They're really close to each other, but they don't match up exactly. Okay. All right, so now using function notation. So what's the notation for an inverse function? Remember? F what? So if I have f of x for my function, so if x of x is 2x plus 3, what's the inverse? F inverse of x is x minus 3 over 2. Guys don't remember that? My gosh. So if f of x is the cube root of x, then f inverse of x is x cubed. Okay, so inverse notation is f to the -1 power, basically. Now that's not a mathematical function, it's just simply a notation. It's a way of writing it, okay? All right, so we're good at working with exponentials if the exponent is not a variable, right? We've done that. We can do x squared, 5 cubed all the time. Okay, so quickly, 2 cubed is 8, good. 3 squared, 9. 4 to the negative 2, 1 over 16, good. 16 to the 1/2, yeah, it's just a square root, right? So that is 4. 10 to the 3rd, how about 1,000, right? You write down that many zeros. All right, now what if the exponent is a variable? Okay, 3 to what power is 27? 3, okay, that one's doable. 7 to what power is 343?
7. I just guessed.
I know, because that was way wrong.
3.
7 to the 3rd power is 343, good. 16 to what power is 4? We just did it, right? That's the 1/2 power. 2 to what power is 8? 3rd power. 4 to what power is 21? Ooh, tough one, right? We can't just crank that one out. So, we need a different way of writing things, okay? We need a different method to be able to solve a problem like that. Okay, all the others we were able to get because we knew our powers really well, but we never actually solved for x. We just intuitively, or through lots of repetition and practice, knew what those were. Am I fair in that assessment?
Yeah.
Okay, that's pretty fair, right? Okay, but we never did solve for x for any of those. So now we need to learn how to solve for x when x is in your exponent. Okay? Now the problem is we don't have any tools right now to bring that x, get that x out of our exponent. And I'm going to give you some of those tools right now. So, we need something that basically undoes an exponential, right? We've already talked about subtraction undoes addition. Division undoes multiplication. Square roots undo squares. Well, what undoes an exponential? It's called a logarithm. Okay. Logarithms undo exponentials. And basically, really all logarithms are is another way to write an exponential function. But we can write it in such a way that we can solve for that exponent, and that's what's key about logarithms, okay? So now there's 3 parts to an exponential. Shh. Okay, we have the base is b, the exponent is x, okay, and the expression is n, it equals n, and this is read exponential base b. Now, we can rearrange those same 3 parts and make a logarithm equation, okay? Now, the cool thing is that the base of the exponent is the base of the log. That doesn't change, so it's logarithm base b, or log base b, okay? Now, here's the deal. Logarithms are always equal to exponents. So what's my exponent? It's x, so if the log is equal to the exponent, the x always goes over there. Well, then we got 1 spot left for our n, right? So that's log base b of n equals x is how you would say that, okay? And we're going to show you how to do those. Okay, so now we're obviously more familiar with exponentials than we are with logarithms, right? For some of you, this is probably your first foray into logarithmic expressions, okay? But if you remember 2 things about logarithms, okay, it'll really help you understand them and make them easier for you, okay? Fact number 1, logs are just another way to write exponentials. So all we're doing with a log is we're rewriting the exponential. And number 2, the answer to a logarithm is an exponential. Or is an exponent, I should say.
Wait, did you teach us to last year but you didn't finish?
Right. Yeah, we got partway through it and then we ran out of time, never finished it. Okay. Okay, so both exponential form and logarithmic form have their advantages, and you're going to see that as we go. It's good to be able, and in fact, it's critical to be able to convert back and forth. If you can't, you're going to struggle on the final exam. I'm going to tell you right now. So you've got to be able to convert back and forth from exponents to logarithms.
Did you finish the last example?
I thought I did. Did I not?
I know.
Called putting the cart before the horse, Emma. Right? We don't want to put the cart before the horse. We don't want to eat the meat before the milk. You're going way, in other words, you're going way too fast, dear, right? You don't serve a baby steak. You gotta give it milk first.
Oh, okay.
You go simple, and then you go on, okay?
What? Okay, moving on.
All right, at any rate, okay. Okay, you can't put, when a horse has to pull a cart, you can't put a cart in front of a horse and expect it to move along, all right? The horse has to be before the cart. See, Emma's trying to take our cart and shove it up in front here and learn how to do that before we know how to do the basic stuff. So, that's the cart, the horse has to go before the cart. There we go. There's your old-time expression lesson for the day,
Thank you.
okay? All right, so now let's work on converting back and forth from exponential to logarithmic form. Okay, so if I have 2 to the third equals 8, let's put that in log form. So that's going to be log base, what's the base? Base is the same, 2 of 8 equals 3. Good. Okay, 4 squared equals 16. Log base 4 of 16 equals 2. 2 to the negative 5 equals 1/32. Log base 2 of 1 over 32 equals negative 5. 9 to the 1/2 equals 3. Log base 9 of, oops, I wrote that wrong. So the base is 9. Log base 9 of 3 equals 1/2. Good. 16 to the negative 1/4 equals 1/2. Log base 16 of 1/2 equals negative 1/4. And the last one, e squared equals x. So log base, oh yeah, you're going to see e again. Log base e of x equals 2. Okay, y equals 10 to the 5th. So log base 10 of y equals 5. Good. Okay, so log base 6 of 36 equals 2.
6 to the second equals 36.
Excellent. 6 to the second equals 36. Log base 3 of 27 equals 3. 3 to the third equals 27. Good. Log base 9 of 1/9 equals negative 1. So 9 to the negative 1 equals 1/9.
Isn't that like 1/9 equals 1/9? I don't know, sign up for 1.
Well, yeah, they're all that way. Right? Okay, log base 10 of 1/1000th equals negative 3. So 10 to the negative 3 equals 1 over 1,000. Log base 9 of 3 equals 1/2. So 9 to the 1/2 equals 3. Log base e of 31 equals y. So e to the y equals 31. And then our last one here, x equals log base 5 of 12. 5 to the x equals 12. Very good. Okay, let's read for a little bit now. It says, being able to change between the forms can and will be extremely useful for you, okay? And always remember this, if you're having trouble in exponential form, put it in logarithmic form. If you're having trouble in logarithmic form, put it in exponential form, okay? Changing the expression to a different form can sometimes make that answer a lot, and oftentimes will make the answer a lot more apparent, okay? You'll know how to solve whatever variable that you're looking for. Okay, so a log is basically asking a simple question. It's asking, okay, for the exponent that goes on the base to make the correct answer. So in other words, 2 to what power is 8? Well, that's 3. Or log base 2 of 8 equals 3. Okay, that's what it's asking. Okay, it's a lot like square roots, right? Square root of 25 is just asking what number squared equals 25. Right? What number squared is 25? It's 5. Oh, so the square root of 25 is 5. See how that relates to each other? Okay. So again, log base 2 of 32 is asking 2 raised to what power, to what exponent gives you 32? Okay. All right, so let's look at example 3 now and let's evaluate these logarithms. So log base 2 of 8. So in other words, 2 to what power is 8? 3. Good. 2 to what power is 32? Somebody say 5.
5.
Right? 2, 4, 8, 16, 32. 10 to what power is 100?
2.
2. 10 squared is 100, right? 7 to what power is 49? 2. 16 to what power is 4?
2.
Eh.
Over
1/2.
1 over 2, or 1/2. Good. Okay, 1/2 is just like a square root, right? Okay, 6 to what power is 1 over 6?
-1.
Negative 1, good. 3 to what power is 1/9? Negative
2.
2. Okay, 17 to what power is 1?
0.
Good.
How did you guys get 0?
Because what's anything to the 0 power? 1, there you go, that's how. So whenever this number right here is 1, what's our answer? 0. Good. All right. Okay, so now we're going to find some inverses here of our exponentials. So look at example 4 now, okay? It says, find the inverse of y equals 2 to the x by switching x and y and solving for y. So now I get x equals 2 to the y, correct? Now if I'm going to solve for y, I got to get that y out of my exponent, right? So how am I going to do that now? We're going to use logarithms. So we have log base 2 of x equals y. There we go. Now we just solve for y again. There's your inverse. So exponentials and logarithms are inverses of each other. Okay? That's what we're getting out of here. Exponentials and logarithms are inverses of each other. So if we know that, okay, now if we want,
You change it from y equals 2x to x equals 2y.
because we said to switch x and y.
Oh,
Because I actually followed the directions. Weird how that works, I know.
crazy.
Okay? All right, so the function is inverse using function notation, so just get used to this. So our function notation then would be f of x is 2 to the x, and then inverse, which is f inverse of x, is log base 2 of x. So again, exponentials and inverses, or exponentials and logarithms are inverses of each other. Exponentials and inverses are logarithms of each other. Wait, what? All right, so now let's graph them both. So we already know how to graph y equals 2 to the x, right? That's pretty simple. So we're at, oh gosh, this is hard. Okay, hold on. I've got to blow this graph up. Okay, so we are at -1 and a half, 0 and 1, and 1 and 2. There's our exponential. Okay? Now, if we're saying that logarithms are inverses, I can just switch x and y. Right? That's all I have to do. So instead of -1 and 1/2, I have 1/2 and -1. Instead of 0 and 1, I have 1 and 0. And instead of 1 and 2, I have 2 and 1. So here's what my logarithm looks like.
So it's just flipping the x and y's.
Yeah, we're just switching x and y. Okay, and remember, a graph and its inverse are symmetric about the y equals x axis there. So if I took that black equation, flipped it over the red line, I would have the blue graph. Okay. So now, with our black one, with our exponential, what's our asymptote?
0.
Y equals 0, right? With our blue one, with our logarithm, what's my asymptote now? Y equals 0. Or no, it's not y. X equals 0, right? Because we just switch x and y. So remember, with the black one, what's our domain? Yeah, negative infinity to infinity. What's our range?
0 to
0 to infinity. Okay, now let's look at our blue one. What's the domain of our blue one? Look at the range of the black one. 0 to infinity. Hey. Because if we just switch x and y, we're just switching domain and range, right? That's all we're doing. What's the range of our blue one now? Yeah, look at the domain of the first one. There we go.
Gosh,
This is like,
we learned a lot today.
we have,
Yes, we have. I know.
2 pages.